Okay, in the last video, we looked at what causes vapor pressure in a liquid. And I want to take that a little further this time. And I want to explain to you what is the effect of temperature on vapor pressure. So, effect of temperature on vapor pressure. So suppose we increase the temperature of a liquid. What would happen to its vapor pressure? And we find universally that vapor pressure increases as temperature increases. And we'd like to say, well, what's the explanation for that? How do you explain that? And so let's think about, well, what happens when we increase the temperature of a liquid? What happens to the molecules? Well, the molecules of a liquid move faster. So they are moving faster. And if they're moving faster, then more of them can overcome the intermolecular attractive forces. So if you like, a greater fraction, a higher percentage, more molecules overcome the intermolecular attractive forces. Because the intermolecular attractive forces really don't change with temperature. I mean, they're not temperature dependent. I don't know, it kind of reminds me of those movies, you know, where a truck being driven very fast goes through the gate, you know, and these guards fly off in different directions. They might be good guys, they might be bad guys, I don't know, you'd have to see the movie. But anyway, what's my point? Well, the strength of the gate isn't dependent on how fast the truck is going. But the faster the truck is going, the more easily it can, quote unquote, overcome the resistance of the gate. So the gate is a bit like intermolecular forces. Faster you move, easier to overcome. So what happens? Well, what happens then is that you now have a greater escape rate. Greater escape rate. And if there's a greater escape rate, what does that lead to? Well, you've got more molecules in the vapor phase, so that means that there'll be more molecules returning, so that leads to a greater return rate. Greater return rate. And eventually what happens is, it's kind of like we saw in the last video, eventually what happens is the two rates become equal, and you have another dynamic equilibrium. The escape rate, I'll just call that ER if you like, equals the return rate, RR, and so you have a new dynamic equilibrium. If it's a new dynamic equilibrium, well, what's the difference between that and the one we had at lower temperature? Well, the difference is that you've got more vapor. You know, you just have more molecules or more moles in the vapor phase. So if that's true, doesn't it make sense that the vapor pressure would be higher? So, you know, it depends on the number of moles, so the vapor pressure has increased. You know, it's a common mistake among students to think that vapor pressure increases just because of the, you know, ideal gas law. But that's not the principal reason. The main reason is you're just making more vapor. If you like, the number of moles is increasing. Well, what exactly does the dependence on vapor pressure look like? I mean, if we were to draw a graph, is it a straight line? Is it, well, what is it? Well, let's say I draw a graph here, and let's say we call this vapor pressure, and this is temperature, and it could be degrees C, doesn't really matter. And let's suppose that we have some liquid. This is very typical. It starts out fairly small and then rapidly increases. So that's very typical of a vapor pressure for a liquid. And I'm going to write a special pressure here, 760 torr, which of course you'll realize and recognize as being 1 atmosphere, one 1 atmosphere. Okay. If I trace this over to see what that temperature is, this will be the temperature at which the vapor pressure of the liquid is equal to 1 atmosphere. Well, if you have an open system, it means that the vapor pressure of the liquid is equal to the external pressure, and so this is actually the boiling point, because bubbles will form in the liquid, and they're going to keep forming because their pressure matches the external pressure. So you're getting a lot of bubbles. Last time I checked, that was boiling. So this is the normal boiling point because it's the boiling point when the external pressure is 1 atmosphere. Well, now let's suppose we have a different liquid. And, I don't know, maybe it looks like this. You can see that its vapor pressure is increasing much more rapidly. And so its boiling point is going to be quite a bit less than the first liquid. So we'll say here. Well, why would that be? Why would its vapor pressure increase more rapidly? Well, clearly, it must be easier to separate those molecules. And if it's easier to separate the molecules, the intermolecular forces must be less. You don't need as much energy to pull them apart. So the greater the intermolecular forces, the higher the boiling point's going to be. Is there a relationship mathematically that describes these curves? Well, there is, and the equation is known as the Clausius-Clapeyron Equation. And what it says is it relates pressure this way to temperature. The natural log of the pressure at temperature number 1, or pressure number 1 over pressure 2, is equal to delta H of vaporization. In other words, the heat of vaporization, the enthalpy of vaporization, divided by R, the gas constant, times 1 over T2 minus 1 over T1. And these, of course, are the two temperatures. The temperatures have to be in Kelvin. I'll give you an example. I've written out a problem here that we could look at on this sheet. And it says benzene, C6H6, has a normal boiling point of 80.1 degrees C. If its heat of vaporization is 30.77 kilojoules per mole, calculate the vapor pressure at 30 degrees C. So we can write out the Clausius equation for this. Do we know any of the pressures? No, we don't. Or do we? Wait a minute. The boiling point was 80.1. What's the vapor pressure at the boiling point? You got it, 760. So 760, it doesn't matter which one's on top as long as these temperatures correspond correctly. This is going to be 30.77 times 1,000. Why? You got to change it to joules because R is written as 8.314 joules per mole per Kelvin. So it's important to get that right. These temperatures in Kelvin are 303. I mean, we're just adding 273 to Celsius. 353.1. Well, let me see if I can get my trusty calculator going here. 1.733065 and some change. So 760 over P2 will be E to all of that, which I'm going to hit second ln, or E to the X, and that's 5.657969. So P2 will equal 760 divided by 5.657969. And if we do that, I'm just going to hit reciprocal of that times 760, and we get 134 millimeters of mercury, or 134 torr, for the vapor pressure of benzene at 30 degrees.